The goal of the project was to design a multifunctional pavilion for temporary cultural events, and also to design a parametric workflow enabling the fabrication of complex shapes using simple units. In other words, fabrication of free-form double-curvature surfaces using planar members. The seat of the parametric engine would be a single reciprocal frame cell, and its engine would be a triangle tessellation of that seat onto a double-curvature surface based on the surface's normal vector directions. Tehran's City Theater Plaza was selected as the site for this project because of its cultural significance and the fact that this site hosts many frequent temporary events throughout the year. And thus, a parametric model was developed that would discretize a double curvature surface into smaller triangular units. After being structurally optimized using the kangaroo engine, each triangle would be converted into a single reciprocal cell. However, this method would result in reciprocal structures with undesirable discrepancies. In order to fix this issue, all of the reciprocal curves were extruded in the direction of the double curvature surface, resulting in reliable intersections. These intersections then would be turned into reciprocal structure members, and the space in between them would be used for sunshades. A custom C# script was also developed to facilitate the fabrication process. The whole structure is sorted from the bottom towards the top, and each member can be highlighted in its place on the computer screen. To further understand the structural system, a physical mock-up model was built. After experimenting and interacting with the model, the following points were discovered. First of all, without supports on the outer edges of the structure, it would not stay upright, and it would slope down towards the ground. Second, there is a need for a locking mechanism that would keep the structure's shape in place. And third, as the height increases, the members would start to look more and more alike, providing an opportunity to standardize the structure substantially while retaining its shape. It seems that all of these findings are directly connected to the tolerances that were implemented in the project to facilitate the fabrication process and assembly. The first point can actually be beneficial to the fabrication process. The whole structure can be assembled in a sequence of lift-ups and assemblies. This would allow for adjustments in the position and the number of lift-up anchor points in an intuitive way as well. While the supports are being placed at the final stage, the locking mechanisms can finally be placed and inserted to fix the final shape of the structure. Of course, holographic guides such as the Hologram software and the HoloLens could significantly simplify the assembly process. With regard to sunshades and the locking mechanism, it was observed in the physical model that the hexagonal cells would expand in size when the outer supports were not in place. This means that the sunshade members need their arms to extend more to make sure that they would stay in place during the initial assembly. After the lift-up, pins can be placed in the corresponding holes to keep the structure in place. Another lock system was also implemented on the member endpoints to make sure that the structural members would not slide out of their holes. With regard to standardization, it can be observed that both in the digital model and the physical model, as the height in the structure increases, the structural members will start to become more and more similar. In other words, it seems that it is actually the members closer to the edges that are building the curvature of the surface rather than those on the top. For this matter, a complete C# class was developed in Visual Studio that would include all the necessary properties of each individual structural member. These properties would include the member's hole center points and diameters, the position of the corners in 3D space, and a spatial plane that the member is placed in, and especially all of these points and corners with their local and relative coordinates in that spatial plane. A class method was developed in the C# class that would calculate the numeric difference between two structural member instances, determining whether they would be interchangeable within a certain tolerance or not. By using this class, it was discovered that 5 types would be enough to standardize the upper part of the structure. However, geometrically speaking, it is impossible to standardize the lower parts of it, as it would substantially change the target shape. In this instance, the structure's unique member count was reduced to 5 types and 319 unique lower part members, while the original member count was 676 members. The parametric model has one additional feature that is fairly related to standardizability. It offers the option to choose between standardization or structural optimization. In the end, this structure type would be ideal for temporary events, as it would offer easy and low-cost fabrication with great flexibility in terms of the geometrical form, compared to other methods that may require high accuracy in the assembly and fabrication. Reciprocal frames would offer a much more flexible and easier to work with option.